Thank you, and thank all the organizers. I was asked to address a few questions. The third one I will skip entirely because I don't have anything to add. The first two I will try to pay attention to. So the first part of the talk will address these two questions, and then at the end I'll sort of address the questions I wish I were asked that I think might be relevant to somebody. So we can see if any of these stimulate good discussion over the next coffee break or dinner or tomorrow. So I think that the basic challenge that I got a sense of was you have a multimodal likelihood when studying a microlensing light curve, maybe even some astrometry data, and that's challenging because you have to be able to navigate, first find multiple local maxima or minima depending on how you phrase the problem. They may be widely spaced. In between them may be deep valleys. Some of them are sharp and narrowly confined. All of that is just mildly annoying in low dimensions and gets progressively harder as you go to higher and higher dimensions. So we can ask, well, where else has this been had similar problems? Of course, there's many fields of science and not just science that have these, but for purpose of our conversation, in exoplanet searches, we have similar challenges in radial velocity data, also in astrometry, as Alexandra told us this morning, transit searches, transit time variation. So I'll give a few examples of where we've had similar issues and maybe help identify parallels. Okay, so what's common across all these different planet search methods? All of them have a nonlinear likelihood. All of them, it's highly multimodal, particularly in the orbital period. And there's typically of order 5 to 7 parameters per planet, depending upon what assumptions you make. And also a common problem is there's an unknown number of planets. And your prior might be, there's probably several planets, even before I take one piece of data. But you're not asking what do you think the number of planets is. You're saying, what does my data provide evidence for? And so it's kind of this awkward situation where your prior might actually be, there's probably several planets, but my data only tells me there's evidence for one. And so effectively, you're marginalizing over the influence of all the planets that you haven't detected. In some cases, like transits, where there's basically no signature for the non-transiting planets, that's relatively trivial. But in cases like astrometry or microlensing, where there may be some effects, it may be more important. Another similarity is that in most of these cases, we can assume the planets follow Keplerian orbits for the vast majority of cases, some very interesting exceptions. And in your case, you may even be able to get away with even simpler assumptions about their paths. So the basic strategy for dealing with these hard parameter spaces is to break up your problem into two sets of operations. One is explore, look broadly, try to find anywhere that may be interesting to explore in detail, and then exploit your knowledge about each of those individual local minima to sample from them very efficiently. So we'll start with the explore phase. The first thing you want to do is use your physical intuition to help make it easy for the explore process. And then once you've done all that, then you resort to computational power to plow through it. So, for example, we might say, well, technically a planetary system is following n-body equations of motions. I mean, you could go extreme and worry about relativistic effects, quadrupole moments, right? But for most of our purposes, those higher order effects are not relevant, and we can treat it as Keplerian orbits. In many cases, even though there's a small number of very interesting, highly eccentric planets, the vast majority of what you're searching for are planets on reasonably low eccentricity orbits, and you could probably get away with something like an epicycle approximation. That may make more things linear, and we'll see later that linear parameters are highly advantageous. In some cases, you may even be able to get away with circular orbits, coplanar orbits. Those sorts of assumptions may allow you to more efficiently search through parameter space because you're able to effectively collapse dimensionality and get rid of a few parameters. Again, this is just for the explore phase. At the end, when we do our inference, we can always bring back those extra parameters, but during the explore phase, those assumptions may be quite useful. In the case of microlensing, I wouldn't be surprised if often you could get away with even simpler assumptions, like maybe the trajectories are linear or quadratic for some amount of time, depending upon the event duration. The next step is once you've written down your model and whatever assumptions you're willing to make, is to sort of think of those parameters and try to organize a hierarchy. There's hopefully 1 to 3 parameters that are really important, highly multimodal, and you know what, I just am going to have to search over them brute force. That's just the way it is. If I don't like it, tough. But then there may be other nonlinear parameters that still are interesting, and maybe there's 2 modes, but they're fairly broad, where you have to worry about them, but they're sort of secondary importance. And a good optimizer, for example, might be able to deal with those very efficiently without resorting to a full brute force search. Then you want to identify which parameters can I write the likelihood in a way such they have a linear dependence upon these parameters, or maybe a nearly linear dependence upon these parameters. Sometimes you're working directly in the likelihood, sometimes you're thinking in terms of the posterior density, and sometimes you can play little games. And for the purposes of the explore phase, you might adopt a set of interim priors that aren't the real priors you want to use, but ones which allow you to write the problem in a way where your posterior is a linear function of certain parameters. Therefore, you can much more efficiently search that, and then later you can back up and worry about putting in the priors that you actually want to use for your analysis later. A fourth type of parameter is a nuisance parameter. This could be things like the noise model. Technically, when you have a bunch of data points, every little measurement has an error vector, right? And often we sort of just lump those together and think, oh, there's one magnitude of the noise, or maybe. But whenever you have these nuisance parameters, particularly if you have more complicated correlated noise models, maybe you have other stars in the same frame you're using to help remove instrumental systematics. We often can treat these very efficiently because they make a relatively modest contribution each. Okay, so for the key multimodal parameters, basically brute force is the only option. For orbital period, this is what we do all the time in the radial velocity astrometric transit timing regime. If it's a problem, there are opportunities to get very big speedups. Well over a factor of 100 is not uncommon with GPUs, and they're getting increasingly easy to program for. The main requirement to be able to get a good performance benefit is you have a high ratio of computing you need to do on the amount of data you need to load. So if you have a relatively small model and can do lots of operations on it to compute your data set, that I suspect could be a very good application of GPUs here. Next, you have or on the other extreme, sort of the linear or nearly linear parameters. Here, if it's truly linear, you can literally find the optimum with linear algebra. You can even marginalize over it with linear algebra if you make some approximations like extending integrals to infinity and assuming Gaussianity. Oftentimes, even if you're not going to use those approximations for your final inference, again, for the explore stage, extending limits of integration to infinity gives you a humongous performance boost and has a marginal cost in mapping out the posterior distribution. So marginalizing with a Laplace approximation is often really good. Some cases where it's a little bit tricky, you can use what's known as nested Laplace approximations, where you pick sort of carefully which variables do I need to do first, and maybe you have some parameters you use Laplace approximation for to calculate one marginal, and then iterate over that at a higher level if you have a hierarchical model, for example. Then there's the other nonlinear parameters. These are kind of the ones that are a little bit annoying. You might use an iterative optimize over it, use an algorithm, but maybe you don't actually run it, say, 50 iterations like you would if you were in the exploit stage. Maybe you just need to get close enough to the maxima to know sort of what's going on there. So you might use a fixed number of iterations. You might be able to use a pre-computed quadrature grid. If, for example, I'm integrating over the argument of pericenter, well, at 0 to 2 pi, I can kind of figure out how dense my sampling will need to be, and I can use an efficient quadrature grid to integrate over something like that. So oftentimes we can sort of use our physical intuition to develop an effective strategy for marginalize over those, making use of the unique aspects of each parameter or model. One thing that's kind of high is that different parameterizations of the same model can be easier or harder to search. So it's very useful to identify those linear parameters. We heard from Alexander this morning. If you kind of saw, he had 4 little functions. I forget where they were, F, G, A, B or something, about how you could take 4 parameters from the astrometric model and make it linear in them. It's one of those things that's kind of clever. Once someone figures it out, it's easy to take advantage of. So do think about opportunities like that in your models. Okay, so for some examples. In the context of radial velocities, our key parameters, the orbital period, the likelihood is ridiculously multimodal in that. We have no choice but to just brute force explore all the periods we're interested in. A relatively naive implementation, you can get 2 radial velocity amplitudes per planet where the likelihood is nearly linear, also the instrumental offsets, but your eccentricities and one of the angles per planet and any sort of hyperparameters in your noise model would enter nonlinearly. However, if you're able to change the way you write the functional form, you can also write in a way in which the RV amplitudes are nearly linear in 4 parameters, at least for low eccentricities. By doing that, you're then able to both optimize and marginalize much more efficiently and sort of drastically reduce the number of nonlinear parameters you need to deal with. In the case of transits, here it's a little bit harder. We have the orbital period, phase, and duration, all of which are very important, and there's no way to be clever about. So we have a very dense grid in period that we search, a dense grid in phase, and a kind of not so dense grid in duration. So recognizing that the width of the posterior in terms of that is broader than in the period and phase dimensions. We can still use our physical intuition to figure out the sampling and frequency space and the sampling and phase at each frequency that's necessary to not miss modes. And in this case, for example, the resolution in phase depends upon the frequency or period you're searching, and by adjusting that as you go to different periods, you can get a very substantial speed up, even in the order of your algorithm, compared to if you fix that phase resolution. So sort of thinking through your problem like that can help you identify ways, little tricks for those key parameters. But once we've done that, things like the transit depth, and also if we're removing long-term trends, we can write that in a way where it's linear in those parameters, allowing us to very efficiently integrate over those. In some cases, there's some noise that's not part of our measurement uncertainties, and we have a noise model that has nonlinear parameters. For example, if the star has some astrophysical variability that's not modeled, we might have a correlated noise model with a correlation strength that's a nonlinear parameter and has to be optimized over in that case. Okay, and transit timing variations, again, we have key parameters of orbital periods and phases. It's interesting, there's actually some pretty complicated correlations between masses and eccentricities and pericenters. If you write it in the right way, it's actually a pretty simple Gaussian. If you write it in the wrong way, it looks really nasty. And so this is a case where sort of being careful how you parameterize your problem can make a big difference. Typically, we ignore mutual inclinations and nodes. Technically, they're sort of nuisance parameters, but in most cases, they're small enough mutual inclinations that we can sort of get away with just exploring the coplanar solutions during the explore phase. A few other sort of thoughts about how you can use your physical intuition to help. You may have a complicated model that's expensive to evaluate, but once you evaluate that model, you can view it from several different orientations. And so in that case, you can evaluate your physical model once and then compute either how it would appear to observers in different places, or maybe just derivatives of how it would appear to observers near the line of sight currently being considered, so that you're able to sort of extract extra information about that one expensive model evaluation. Often there's small eccentricities or small inclinations that also allow you to sort of not solve, for example, the full Kepler equation, but use a series expansion that would be much faster. Okay, so let's assume now that we've successfully explored parameter space and we found the regions where there are any modes that we're interested in. So we no longer have to worry about missing modes, but the modes we found may be disparate, they may be nonlinear correlations, and sort of non-Gaussian. So what do? Well, first, I want to ask, what do you really want to do? The way some people pose the question to me makes it sound like they want to find the best fit solution. And sometimes that's a useful and interesting thing to do, but often it's not your real science goal. Often you're asking, what can I exclude? What things near here are so bad they're rejected, rather than what happens to be the best? And that's related to finding your sort of uncertainty estimates for your parameters. So I would phrase that typically as the difference between finding an optimum and then drawing a posterior sample in the region around that local mode. And typically MCMC is the sort of workhorse algorithm for that posterior sampling. You actually can also use importance sampling. Sometimes there are advantages, particularly if you have a good sense that a particular mode will be relatively easy. Maybe you think this mode actually is nearly Gaussian, or maybe it's relatively simple to use. So there may be chances where you can use importance sampling. I find it's just simpler in a lot of cases to use MCMC, so I don't have to bother checking and worrying about it. But there's one case where importance sampling really shines, and that is if you want to marginalize over those parameters to ask a question like, is the evidence for this little bump being a planet significant or not? Now you need to do not just parameter estimation, but model comparison. And for that model comparison, typically if you can do importance sampling on it, you'll be much more efficient than if you try to jerry-rig some MCMC strategy about it. Of course, these can be combined. So, for example, you might combine an importance sampler with an MCMC scheme to deal with a multimodal strategy. For optimization, one thing that I think a lot of people don't take advantage of is making use of gradient information. So when you have a one model, oftentimes it's not that much more expensive to compute derivatives of that model with respect to some or all of your parameters. In particular, the Kepler equations, which at first seem like they have non-differentiable points near 0 and 1 and so forth. There's a very nice, clever expansion of the Kepler solution for the either astrometric or radial velocity path of a planet by PAL that allows you to be fully differentiable all the way through 0. And once you do that, you can then have gradients of your likelihood. Also, there are cases where if you ask a computer to use auto-differentiation, which sometimes is really convenient, it will come up with some very expensive and convoluted way of doing it. But if you just play with the equations a little bit, you can help it differentiate the Kepler's equation yourself. If you're using a really powerful auto-differentiation package, you can actually tell it, don't worry, this function I'm telling you how to differentiate, and it will use that information so as to make more efficient trees for calculating the auto-differentiation for you. So if performance on the optimization side is an issue, those are tricks you may want to be aware of. Once we get to the posterior sampling phase, there's sort of two styles of MCMC. I'll call one the artisanal approach, where you look at your parameter space and you think about the equations that cause the curvature. You map it out and you go, oh, I can understand. That's due to the degeneracy in square root m and 1 over distance to length here. And then you use that information to design a sampler specifically for your problem. And sometimes this can be useful, particularly if there's a near degeneracy, where the natural parameterization, there may be some complicated banana sickle cell shaped like posterior that's annoying to sample from. But if you're able to make use of the functional form that causes that degeneracy, you can then sort of find a reparameterization where it becomes nearly Gaussian, nearly orthogonal in the different parameters. And if you can do that, then you can get a nice performance speed up, regardless really of which algorithms you're using. This could also be particularly useful in the case of multimodal models where you have, or data sets, where you have one solution over here, one over there, and you want to be able to jump between these two solutions efficiently. Well, you can just say, I want you to, every 100th step, try jumping from here to there. And if you put that in, now your algorithm won't be so bothered by the fact there's multiple modes. The downside is you have to write a proposal function that allows it to jump from one mode to the other. That requires a little bit of thinking. Maybe you're looking at an individual data set. So at least so far, I've only seen this done on people looking at one system at a time, as opposed to, say, analyzing all the microlensing events from campaign 9 or something. Right, so when you do use funky parameterizations to help with degeneracies, do be careful at priors. So sometimes it is convenient to choose uniform priors just because it probably won't really matter. But you can definitely get in cases where once you're using these proposals that were designed to exploit some funny shape, you can do some really funny things to your priors if you're not careful. So make sure you include both the terms in the Metropolis Hastings acceptance for the priors that, or at least you're trying to use at the time. So that's the artisanal approach. It's very nice if you want to spend time doing it. Sometimes life is busy and you just want something that kind of works. And in many cases, these ensemble MCMC samplers do remarkably well. And so if good enough is what you're aiming for and you don't want to spend your time worrying about the particular details, particularly once you're down to 1 or 2 modes, then something like differential evolution MCMC or with a single mode affine invariant ensemble sampler can be quite efficient. And I think the affine invariant sampler was popularized by the MC package. I believe now both of these are available in that same package if you particularly like using Python for some reason. These tend to be very good when your dimensionality isn't that high, so single digits, tens, but as you go to higher and higher dimensions, they can lose their luster. So if you go to really high dimensions, maybe for example, you have a latent model of every random effect, all the little errors on every photometric measurement in your light curve, then you may want to think about geometric algorithms. So these are sampling algorithms that make use of things such as the gradient or even higher order derivatives of your likelihood surface to be able to explore the parameter space efficiently. Hamiltonian Monte Carlo is one of those things that when it works well, it can work really well, but it can also work really poorly if either in the hands of a novice or maybe just someone who hasn't spent the time to tune it just right. One significant advance recently has been the no U-turn sampler that basically sort of makes Hamiltonian Monte Carlo not nearly as sensitive to your parameter choices. So you can use a little closer to a black box and be less likely to get into trouble. There's also some geometric adaptive Monte Carlo algorithms. I think it's fair to say they're still a little bit more experimental, but trying to make use of these higher order gradient information in a computationally efficient way. Of course, these can be combined. So for example, you may use a geometric sampler to explore each mode, but also have artisanal proposals to allow you to jump between modes. Arguably, maybe this is like one big artisanal sampler. Maybe it's really just sort of nesting a few samplers on top of each other. You can certainly find good combinations where you think about for each parameter, is this something where I need to handle multimodality? I'm going to plan for it. Is this something that's kind of nonlinear and I just want it to work, but it may be significantly non-Gaussian and I want to have these few parameters explored very well? Or is this something where there's a whole bunch of minor variables that individually don't matter much, but I do want to sample over them? And so by thinking about which category the variables fall in, you can design a nice custom sampling algorithm for yourself. One question that was posed was, what do you do when you have multiple nearly degenerate solutions, and how do you weight them? So my answer is it's kind of not quite the right question. It comes out naturally. If you can just sample from your posterior, the answer is the answer. Now, sometimes that sampling is hard, and you just spend some time doing it. Maybe sometimes you even give up, and then maybe you want to come up with some heuristics. But my formal answer is it just comes out whatever the posterior is, that's the posterior. Now, the thing to be careful of is sometimes, as an astronomer, you use your intuition and say, well, wait a second, that doesn't seem right. And what you're really saying is the likelihood you put in, the noise model you assumed, you don't really believe it, right? And so if you say, well, actually, yeah, I told you those were the measurement uncertainty, that's really just the measurement uncertainty they report. The true uncertainty also has some other effects that I didn't tell you about. And so then you start to a case where once you allow for either additional noise or correlated noise, maybe extra signals such as extra planets, stellar variability, background objects that could inject a temporally variable signal, then that can change the relative weighting between those modes as well as their locations. So in theory, you would just have a model that modeled everything. Of course, in practice, that's harder than one sentence makes it sound. So I think the real solution is, if you're worried about this, is to explore the sensitivity of your posterior to various choices you could have made. So maybe you try assuming there's no stellar variability. Maybe you put in a stellar variability model. Maybe you assume there's no background objects. Maybe you allow the background object to have some sense of variability and see how much that changes those relative weightings and see if your scientific conclusions are robust to those possibilities. So that's sort of wrapping up what I was asked. I do a few more suggestions to consider when posterior sampling. And one is to report what you measure well, even if it's not what the physicists wish you would tell them. So you already do this in some senses. Certainly you're very comfortable reporting, say, the Einstein radius of an event, or things in terms of the Einstein radius of the event. But there may be other cases as well where it's not so obvious. For example, someone today showed the distribution of eccentricities recovered was biased at small eccentricity. This is not something that any algorithm or method will solve. If you have a population of objects which are all exactly circular, anything with error measurements where you're talking about eccentricities will always be biased. So the solution is not to find a better sampling algorithm. The solution is to change what you're reporting. If instead you summarize your data set in terms of E sin omega and E cos omega, now each of those can be measured as positive or negative, and regardless of sort of which particular model you're using, you can have a method that's no longer biased and allow you to do scientific inference in a more responsible way. You can have similar effects for things like inclinations, in some cases even masses, parallaxes. We saw earlier people advocating treating it as measurements rather than estimates of the parameter you want. Another question I thought you were going to ask me was how to find out how many planets were in a microlensing system. And this is closely related to how many planets are in a radial velocity type system as well. I'll rephrase it slightly into how many planets does the data provide strong evidence for. And it's a little bit long to say, so we'll abbreviate that. And so basically, this is asking you to go from your astronomical intuition about what you think constitutes strong evidence to quantifying that and doing what's known as Bayesian model comparison. And this is very powerful, but it also requires going a level beyond what is necessary for simple parameter estimation. In particular, it can be very sensitive to your noise model. Sometimes people like to argue about, oh, does this depend on your prior? And they talk about priors that differ by like a factor of 3. But they don't bother worrying about their likelihood that has a factor of 10 to the 100 in it, right? And forget the factor of 3 in your prior. The main thing to worry about is your likelihood right? And so particularly if you have lots and lots of measurements, and you go, oh, I have all these measurements. Each one is Gaussian. Really? if each one is Gaussian, right? I mean, that's a strong statement. And so you want to be careful when making these inferences about strong statements. So rather than guessing a noise model, at least sort of think about what are the parameters of my noise model. I'm at least going to marginalize over those. And often having some parameters that indicate things like some extra noise or some strengths of correlations can go a long way to mitigating the worst of the sort of spurious discoveries sort of fooling you. So strongly advocate being careful to marginalize over a noise model, or at least do sensitivity tests to see if they're robust to different choices there. In general, Bayesian model comparison is computationally intensive, and that's why it's often not done. There's a significant time in papers you see things about AIC or BIC. BIC particularly, as Bayesian is the first word of the acronym, but that does not mean it's Bayesian. There are asymptotic limits where that applies, but it probably does not apply to your data. So it's really just one particular ad hoc criteria for comparing things. And I think you should be very careful, that particularly if you take thresholds that were suggested by a social scientist in a totally different context and think those somehow are meaningful for interpreting astronomical data. So what are some of the good ways to do Bayesian model comparison? I'll start with the Laplace approximation, or INLA, these nested approximations. They are surprisingly good. Maybe I should phrase as the other methods are surprisingly bad. I don't know, it depends on which day you're looking at. But oftentimes you do a lot of fancy work and you find out you did no better than a simple set of Laplace approximations. So this is basically finding the maximum expanding as a quadratic, maybe including a cubic term in your posterior density, and treating that as a Gaussian integral. And it works quite well. So it's also relatively easy, so you might as well start with that before you go on to fancy things. If you have a reasonably small number of dimensions, sort of 10-ish and below, importance sampling may be a viable option, particularly if your posterior isn't too messy. If you can represent it with a mixture of Gaussians or maybe some t-distributions, maybe write as a product of marginals. The product of marginals can actually scale to higher dimensions if things are really nice, but still important sampling often struggles if you get into significantly more than 10 dimensions. So for some problems where you can marginalize out all the other things and all you have is the last step left, that may be a good option. There's sort of a hybrid importance sampling MCMC scheme that was developed at SAMC a while ago, and I think Ben Nelson's paper on Rho-Cancri is the best sort of description of that in an astronomical setting. I was pleased to see the diffusive nested sampling from Brewer and Ford and Mackey. Looks to me like it has a much better theoretical behavior than the standard nested sampling should that you see in multi-nest. I am not a fan of multi-nest. I'm worried about it. If you've validated it works for your problem, fine. But how are you going to validate it works for your problem unless you solve it some other way? In theory, DNest4 sounds good. I haven't seen it in application enough to sort of get that real-world empirical validation, but I'd love to hear if some people have successes from it. Also, in theory, thermodynamic integration can be useful. It often is quite computationally expensive, but maybe if you're doing things on a GPU anyway, you may find that the extra cost of running 100 times more models than you would before is actually not that big because of the nature of your parallel hardware. So there may be cases where that's useful. About a year ago, at the Extremely Precise Radial Velocity meeting, we had a breakout session with a data challenge. We gave people simulated data sets and asked them to compute the Bayesian evidence or the marginalized likelihood for each of several models, several data sets. I can give a whole talk about that, but I think the key takeaway bullets are validate your codes. It was shocking the fraction of participants who had an embarrassing mistake in their code. These were, highly intelligent, respected researchers who had been doing stuff in the field. Typically, the bug didn't show up in the area where they mostly use their code, but then they were using it for something it wasn't originally designed for, and then right. So always, if you're adapting things, whether it's to scale or just validate those codes to make sure there's not something silly. Another thing we found, particularly with the multi-nest, but several methods that gave an internal error estimate, don't trust them. If there's a Monte Carlo aspect, run that Monte Carlo, the same thing 10 times, and figure out what this scatter in your estimates of the evidence are yourself, rather than trusting the internal ones. They were often off by orders of magnitude. we found that there's often considerable uncertainty in the estimation of the marginalized likelihood, and therefore when you're setting up your experiment or sort of planning how you're going to plan detections, just accept the fact that, yeah, there may be a factor of 100, 1,000 uncertainty. That sounds like a lot, but if the ratio of evidence is going to be 10 to the 100, a factor of 1,000 really doesn't matter. So in some cases it's problematic, particularly if you're trying to barely push the limits of detection, but I'd say just recognize that's yet another source of uncertainty in your pipeline as you go from telescope to discovery. And also, it's good to perform sensitivity tests, as always. Sort of put numbers on what I just said. When we looked at different methods of estimating the evidence, for a zero-planet model, basically it was easy. Everyone got it within a factor of 3. I thought it might have been better than 3, but still, for one planet, for 5-ish, 6-ish parameters, maybe it was 7, I forget. Typically, the different methods gave results consistent within a factor of 10. For 2 planets, depending on which ones you included, like the good ones maybe within a factor of 100 each other, the less good ones maybe a factor of 1,000. And once we got up to sort of nearly 20 parameters, the different methods, different runs of the same method were often differing by a factor of 10,000. So just be very careful when you use these to not take some, a Bayesian evidence of 20 is strong evidence for something. Not if you can't estimate it to within a factor of 100. So do be careful of how you use the estimates of your marginalized likelihood. I see I'm out of time, so I'll just put a plug. If you are interested in talking later, I think one of the big opportunities of WFIRST is to characterize not just individual planets, but planetary populations. And that's also an area where there's been a lot of work with radial velocity and transit, particularly transit surveys. And be happy to talk to you later if they're interested.
Questions for Eric?
One comment, which is one thing that I think differs, having worked in several of these exoplanet areas, one thing that I think is significantly different in microlensing, at least compared to radial velocity and transits, is that the observables are more or less, you can read them off of the data and relate them to the parameters of the model, where in microlensing that is almost never the case. In certain limits, that is true, but many.
But if I phrase the problem in terms of a parameterization that's what you measure well, isn't it still?
Yeah, but generally that means you have to think really hard what the right parameterization is, like the time of the peak of the Costa crossing. That's just a comment. The second is a question. Maybe this is a philosophical question. Why do people use MCMC to find solutions when it's absolutely not designed to do that? It's designed to find the posteriors once you find the solutions. And then the third thing is a real question that I have, which is one thing I've really been thinking hard about is, we're all used to making cuts, delta chi-squared cuts, and now I've detected a planet, and below that I haven't. Of course, this is silly in many ways, right? In some sense, there's planets in all of our light curves. That just might be that the evidence for them is so small that we can't use them. So I imagine there must be a world in which we can use all of the events, all of the microlensing events, or all the radial velocity events, or all the transit events, to do population statistics, including multimodal solutions, right? And evaluate the planet populations using all of the events without using hard cuts, which are totally artificial and depend on the exact error properties of your data. Are there ways to do that? Can you point me to a book? I mean,
Those are two very different questions.
Yeah. Well,
are there ways to do it? Yes.
Well, I mean, can you point me to a paper where people have done that?
So certainly not in astronomy that I'm aware of.
Okay.
But so maybe to rewind first to why people use MCMC for optimization. I think because if you have a code that sort of sometimes it's just easier. But if you plan from the beginning to break up your problem into explore and exploit, then it's not really harder to make use of an optimizer to optimize an MCMC to sample. So I would definitely suggest do that. The only thing I can think of why someone might do it is some optimizers are very good at going uphill or downhill, whichever you phrase it, and do so only one direction. If you have a mildly multimodal likelihood, if you use MCMC either with some tempering or maybe with a noise model that allows for some uncertainty, you can sometimes have it find a neighboring mode if you have weak multimodality. I think in the microlensing case, you're not in that. You more often have really widely separated ones, and if you think that's going to save you, I would think you're in trouble. So I would advocate break it up, explore, optimize, exploit MCMC. The second question is, how do we deal with catalogs where maybe instead of saying here's a subset where we have strong evidence, we want to use all the possible detections, maybe even every object. I think there's probably diminishing information as you go to lower and lower thresholds. So rather than being a purist and literally saying I'm going to search for everything in every light curve, I would probably just set a threshold that was low enough that I thought that anything that had significant information was being included. And then the art of it, I think, is getting someone to design an automated way to set up either a proposal that's able to jump between these different modes, or an important sampler that sort of knows the location each mode to explore. And if someone can automate that process for at least a substantial class of these microlensing events, putting that into a hierarchical model would not be that hard. That would sort of be, the hard part of that will be typically when we use a package, so something like JAGS, for example, assumes everything is some nicely named distribution. That's totally impractical for us. Something like STAN is flexible, and you could jerry-rig to deal with these multimodality. And if you use some combination where you have control over the sampler, so that you could say, I want you to know about these 4 possibly degenerate solutions and be able to jump from one planet to 2 planets and things. In theory, you can do it. In practice, it does require this sort of artisanal approach to be able to navigate those. So I think it'd be a great project for someone to do.
Okay, next question.
More about the differences between a search and a sampling algorithm. So my understanding was that HMC, for example, was like it also found the typical set as well as like sampled from the typical set, and that other algorithms failed to find the typical set and explore it sufficiently well.
So when you optimize, you're literally trying to find where is the optimum, and all you care about is, do you get there? You don't care how you get there, what else you find along the way. And your goal is to end at the optimum. When you sample, your goal is not, you probably never happen to pass through the optimum. Your goal is to explore, to draw from a probability distribution. In most cases, we'd write a prior times the likelihood and say, we want to sample from this posterior probability distribution, and sample in a way such that our samples are proportional to the relative probability of the different solutions. So if you're interested in, say, providing an input to a model that's then going to design some clever sampler, you might want to optimize and find the location of each mode in your data. But then if you want to ask the question, what do I think the distribution is for the mass of the planet, you would want to sample to allow for the relative probability of different masses being the true mass.
Right, but the optimum is far away from the bulk of the probability mass in reasonably high dimensions. Yeah. So, like, choosing an optimum is a poor starting point, I guess.
Well, so for anything that's hard, there's sort of no substitute for brute force. Anything else, you can try to be clever, but if you're clever, you're basically picking some things you're going to tolerate missing. So, if there's something like a genetic algorithm that is sometimes good for global searches, but you're basically being willing to miss things. And so I suspect that the effort required to make your genetic algorithm, do well would be just as well spent in informing how you design that brute force search, and then just Monte Carloing to improve the density in the regions that are most important and decrease it where they aren't.
Okay, I don't. You have a question? Okay, Matthew.
Can you say a bit about what you couldn't talk about, the populations?
That's cheating. Basically, the main thing was, if we characterize populations, you often go to much higher dimensional models. When you have high dimensional models, priors can sort of sneak up because instead of entering once, they're entering 10,000 times, and a small difference then gets multiplied many times. There are tools to help you do it efficiently, but astrophysical complexity often makes it so the standard tools are not appropriate because there's some little annoying thing that you can't really model statistically a standard way. The field basically now is going to approximate Bayesian computing for these sorts of population, where we can include a forward model of the process, including both the survey design and the measurement process. So this means if there was some committee that picked some fields to observe, in theory, you would like to understand how did they pick these fields and what was the probability they might have picked other fields. And then once it goes to actually the telescope, the rate at which you get, I don't know, annoying cosmic rays or asteroids or something sort of contaminating your data. And in theory, you can make it as complex as you're willing to. And one of the nice features is you can sort of build that complexity gradually so that you're able to start with a model that gives you an answer today. It's not the perfect answer. And then you can test each thing individually and say, does adding asteroids, mess me up? Does adding background and the X-rays or infrared or whatever mess me up? And you test these things. And the things you find matter, then you can incorporate the model for real. And things that don't, not.
Okay, we don't have time to more questions, maybe at the break. So let's thank Eric again. And now talk by Daisuke Suzuki about planet.
Can you hear me? Okay. Oh, thanks. All right. I'm Daisuke Suzuki from ISAS JAXA. So I'm going to talk about analysis of MOA 2018 barrage 199, which is equivalent to KMT 2018 barrage 359. So this event occurred this arithmetic, which is indicated in the as a blue star in the right figure. So this field is the one of the ordinary optical microlensing survey field, and so it's far from the expected W first microlensing survey field. So this field is more GB1, which is observed every 47 minutes. So we have a lot of more data for this event. And this event is actually was alerted by MOA on 2018 June 29th. And actually, the peak of the planetary anomaly triggers the alert, the microlensing alert. And 2 days later, Yuki Hirao found a planetary solution for this event. So, and also KMT team independently alerted this event on July 30. And I also checked Gaia DR2 catalog, but so here this is a finding chart of this event, and the yellow circle shows stars in the Gaia catalog, but the target star is not included in the Gaia catalog. So just after the Yuki circulated his planetary model, Dave asked me why you didn't notice the planetary anomaly, because I was an observer at Mountain Observatory at that time. So I'm not sure if I respond that question today, but so here is the actual handwriting Matsu observation log, and I'm an observer at the time, and here is my answer. So somehow I decided this event is binary. So sorry about that, but maybe I need more careful checking, or maybe we need machine learning. Anyway, this event is thanks to the high cadence of MOA and KMTNet, we can cover the whole light curve and also the anomaly part. So we have data of MOA red and V band from MOA, and also three KMT 3 telescopes. So this bottom panel shows the zoom up of the anomaly, and the peak was covered by MOA and also KMT CTIO. So in summary, the event time scale is TE is around 250 days. It's relatively long, so we can expect parallax signal. And actually, this black line is best fit model, including the finite source effect and the microlensing parallax effect. And the mass ratio is roughly 0.01, which indicates a gas giant companion planet. And we have a degeneracy in the separation, so it's wide and close degeneracy because the anomaly was caused by the central caustic. And the finite source effect is marginally detected. The T star, the source star radius crossing time, is measured as 8 hours, but it's the significance is delta chi-square 12, so it's marginal detection. So here, this figure indicates the geometry of the caustics and the source trajectory. And we actually have another degeneracy in U0, positive or negative solution. So we have 4 solutions, and blue, the left here, it's wide solution for S, and the right-hand side, this is a close model. The best fit model is a top left one, so wide solution and U0 negative. And the second best one is a close model with a negative U0, and these are very competitive because the delta chi-square is just 1.8. So maybe I need combine all the solutions, but in this presentation, I'll just use this solution for, okay. So here is a color magnitude diagram, but the magnitude scale is instrumental one for I'm using the more red and V band, and the red clump is here, red clump giant is here, and we estimated the source color with two different methods. One is a light curve model independent color. It's indicated in blue. So for this color, we we did the linear regression of more red and more V. And also another method is just from the best fit light curve model. So this is plotted in green. So these both are these are consistent to each other, but I will use a green point, this color from the light curve model, because it is more consistent with the HSD Boltzmann sequence. So we need to convert the more instrumental scale to the Ogle 3 catalog. Then we estimated the extinction and reddening using the red clump as a standard candle. And we estimated the intrinsic source color and magnitude like this. And so we found the source star is a K-dwarf main sequence in the biology. So using these values, we can estimate the Mueller, the relative length source proper motion, which is theta star divided by T star. So T star is, as I said, T star is measured, the 8 hours, and the theta star, the angular source size, is can be estimated with the empirical relation using the this equation. So we found the Mueller is 0.5 milliarcsecond per year. This is relatively small, short compared to the typical event. But maybe this is typical for the long time scale event, because here this orange histogram is showing the expected Mueller distribution from Han et al. For the microlensing event with TE longer than 100 days. So here 0.5 mass barrier is around here. So it's maybe a typical value. And then we can get the theta Einstein radius as a 0.3 milliarcsecond. It's maybe typical, little bit small, but it's typical. And then we can measure the mass of the lens system with if we can measure the pi e, the microlensing products. So here is the MC chain plot for the pi e components. So we detected the pi e parameters with a significance of the delta chi-square 60. So we can calculate the mass and distance of the lens system. So the host star has a 0.2 solar mass, and the companion object has a 2.6 or 2.3 Jupiter mass for wide and close solution. And the projected star and planet distance is 2.6 or 1.3 AU for wide and close solution. And assuming the source star is 8 kiloparsec from us, the lens system is located at 4.5 kiloparsec from us. So maybe this system belongs to the galactic disk. So so such a massive planet around low mass star is difficult to form based on the co-accretion model, but maybe not too difficult, I don't know. So here, the left panel indicates the recent statistical study which compares mass ratio function from microlensing survey in red to the blue histogram, which is mass ratio distribution from the population synthesis model based on the co-accretion model. So this planet has a mass ratio of 0.01, so which will fall in this mass ratio bin. So actually, the planet frequency in this mass ratio bin can be explained by the population since this is model without migration. But I should note the host star mass in this population since model has a range from low mass star to G-type star. So maybe we should more check carefully. And on the right figure, this is another previous statistical study. And so yes, so as you know, this mass ratio bin is just between the planetary mass ratio function and the stellar binary mass ratio function. So detailed study of around this mass ratio is very important to understand the formation of planet or brown dwarf and low mass stellar companion. So here is on the other hand, there could be two populations of giant planet around solar-type stars. So these two independent studies found possible boundary at around 4 Jupiter mass. Below that, the planet could be formed by the quark accretion, and above the 4 Jupiter mass, the planet companion, these companion could be formed by the disk instability. So we might want to check, study similar thing for the microlensing sample. And here is a left panel is showing the previous mass distribution from Fukui et al. And so this red histogram is the mass distribution for giant planet by microlensing, and the host star is low mass stars. So I updated this figure, which including the recent discovery of microlensing and also this event. So, so original paper implies there could be the deficit of Jupiter mass planet here, but it's for the updated figure, it's not clear yet. So we need a more much more statistical sample, and we also need a detailed detection efficiency study. So in summary, this MOA 2018 Barrett 199 is a planetary event, not binary, and it's a super Jupiter mass planet around low mass stars. So just finishing my talk, I should note lens orbital motion is, I'm still working on the lens orbital motion, and the delta chi-square is not, the chi-square improve, I don't see the chi-square improvement with this model, but maybe we need, I need to consider the uncertainty in each parameters. And also, I should try the binary source model, as Martin and Radek mentioned yesterday. Maybe, and also I should check the model. I'll stop here. Yes.
Can you go back to the original light curve?
Yes.
Yeah, this is just a general sort of comment that it sort of always worries me when I see something like this, that the errors in the data are obviously not Gaussian distributed in this case, right? They're bouncing all over the place, and yet, you know, you and for this model, and also many other people for others, you know, you're extracting a 9-parameter fit to this light curve,
yep,
under the assumption that they are Gaussian distributed errors. Do you have any concerns about this?
Yeah, maybe I need to consider, but for this analysis, I didn't care so much. I just followed the classical manner to normalize the error bar and do blah, blah, blah. So
sorry, this is a comment directed at the whole room, not just you.
Okay, yeah, sorry. Yeah, thanks for the comment.
Next question. Okay, Dave.
Well, just to respond to Michael's comment, I mean, you know, the non-Gaussian errors are the reason why we typically set the chi-squared thresholds much larger than you would need for, you know, Gaussian data. It's not a very sophisticated way, but it's different from totally ignoring the non-Gaussianity.
Plus, when we quote our error bars, we do typically quote, we don't quote delta chi-squared of 20 for our 1 sigma error bar, right? So I think Michael's point is well taken. I mean, I think as a community, we have largely disregarded red noise, which we know exists in all of our data. And it's something that we are going to have to eventually face the music to deal with. So, and yes, we deal with it detection by setting the threshold to have a probability for Gaussian noise of 10 to the minus 5,000 or something. But when we quote error bars, we don't do that. We are careful in quoting different solutions that, if they're different by delta chi-squared of 20, then okay, probably that's not significant, but we're not sure. If it's 200, then it's significant. But by and large, we've basically ignored this problem, even though we all know it exists. I think that's the answer to your question, Michael. I think that's probably the answer you were looking for. Yes.
Last comments from Jen.
Hi, I was wondering what your constraints on rho were. The constraints on the finite source effect.
How significant? Sorry, the finite.
Just what was the measurement in the error bar? Ignoring for a moment non-Gaussian errors.
I can't remember, but it was here it's 8 hours plus minus 1 for T star. Oh, for rho, I can't remember, but oh. Maybe calculate.
Probably
okay.
1/3 error bar.
Yeah.
Like.
Oh, yeah.
Okay, so let's thank Daisuke again. And the next talk is by Iona Kondo. She will tell us about a planet in short time scale event.
Can you hear me? Hello, my name is Iona Kondo. I'm a master student from Osaka University, and I'm studying under Sumi-san and Dave. Today, I'd like to talk about the result of analysis of Morbin 29. And at the beginning, I'd like to talk about this event. This figure shows the right curve of Morbin 29, and green line shows the best point length model, the single lens model. And this event was observed by Moore and Ogu. And this event arrived near peak on 2006. The time scale of this event is about 4 days. So this is a quite short event. And you can see the clear deviation from the single lens model around its peak. And the more data is reduced by the more difference image analysis pipeline, DIA pipeline. And here is the difference image around the event and the difference image during its magnification. And the green cross shows the position of this event. As you can see in the reference image, the source star is faint, and there is a nearby bright star upper left from the event. As a feature of this event was not found in real-time analysis, but found only after the offline analysis conducted by Sumi-san. We can consider the reason. The reason of this overlooking in real-time analysis could be one is the short time scale event, and the second is that the alert system has just started since 2006, so there is a possibility that this system wouldn't work well, or the data of baseline was not enough to fit the single lens model. But maybe we can think another reason. And tomorrow, Hirao-san will talk about these undetected events in detail. And since this event was not alerted, there is no follow-up observation, so the data coverage was poor. But this event located in the Moorfield GB9, which is the highest cadence observation field of 10 minutes. So we can detect the clear anomaly signal. And in order to find the best model, we conduct a grid search. And after grid search, we find that the static binary lens model favors than the single lens model. Red line shows the single lens model, and blue line shows the static binary model. And thanks to high magnification, we can detect the finite source effect. And here is the relation between the mass ratio and delta chi-square. So we find that two competing models as for mass ratio. And next, we'd like to look these competing models in detail. And here is the light curve and caustic of the best model, wide one model. And here is a bump due to the caustic crossing. And the event time scale of this event, this model is about 4 days. It is short time scale event. And the mass ratio is about 10 to minus 2, and separation is about 1.1. And here is one of the competing models, the WISE-3 model. And we can see the bump around 39.22 due to the cusp approach to caustic, cusp approach to planetary caustic. And in this model, the delta chi-square is 5.6, and the event time scale is twice as long as that of the best model. And the mass ratio is about 10 to minus 2. The separation is about 1.8. And here is a summary of all competing models. We find 5 competing models in total. The caustic is divided into 2 types, wide model and closed model by its separation. And the event time scale is of all models is about 3 or 7 days. So they have a short time scale. And the mass ratio of all the model is about 10 to minus 2. So all model has a planetary mass ratio in this event. And here is the right curve of 5 competing models. So the difference between the right curve mainly arises from where there is no data point, like this, or like this. And since we could detect the finite source effect, we can constrain the lens property by using the angular Einstein radius. So this parameter is expressed in following equation, and we can get the raw value from the detection of the finite source effect. And in order to estimate the theta star, the angular source radius, so we have to know the source color and the magnitude. However, we have no V-band data. We have only Moiré band and Ogui band. And in order to estimate the source color, we use 2 methods. One is to derive the color-color relation. In this method, we use a slight difference between Moiré band and Ogui band. And the second is to take average color of main sequence star from HST. In this method, we assume that the source star is the main sequence star. And then we take the weighted average of the color from the 2 methods. Here is the color-color relation. We get this relation by cross-referencing the stars in Moore catalog with the stars in Augur 3 photometry map, and we choose the stars within 120 arcseconds from the source star. Here is the Augur CMD map. Black shows the stars of Augur, and green shows the stars of HST. And pink shows the color from color relation. It has a large error and much redder than main sequence star. And the purple shows the HST, the color from HST. And then, since the color from color relation has a large error, but and consistent with main sequence star within 2 sigma, we take weighted average of 2 color, and the blue shows the weighted average color. And now we got the both color and magnitude of the source star. So we can get the angular source radius. From the collection of reading and extinction from red clamp giant, we can get the extinction-free magnitude and color. And from the empirical formula, we can get the angular source radius. And then in this, by using this formula, we can get the angular Einstein radius. And next, I'd like to talk about the Bayesian analysis. So, since the significant parallax effect was not detected, we can't derive the lens property directly. So, by conducting the Bayesian analysis, we get the probability distribution of lens physical parameters. And to constrain the lens physical parameters, we use the measured T and theta E value. Here is the value of each model. And as for closed model, the difference between the model with finite source effect and the model without finite source effect is within 3 sigma. So we got the only lower limit of theta E. And as for all models, the theta E has a large error. And here is the result. The two figures show the relative probability distribution of the mass of host star, wide one about wide 1 model and wide 3 model. As for wide 1 model, the mean value of the host star mass shows the brown dwarf mass, and as for wide 3 model, that shows the M dwarf mass, and the table below shows the all lens physical parameters of all models. And from this table, we can conclude that the lens system would be a gas giant planet around the brown dwarf or M dwarf. And from this table, we can find that the result of the 5 competing models are consistent within 1 sigma. So we combine the result of lens physical parameters. And here is the result. From the result, we can conclude that we combine the result of Bayesian analysis weighted by its delta chi-square. And then we can conclude that this lens system is likely to be a gas giant planet around the brown dwarf in the galactic bulge. And here is a summary and future work. Thank you.
Radek?
So first, it seems that the best model that you fitted had very large source, which somehow seems unlikely. That's my first comment. And second is more a question. Have you tried binary source models instead of binary lens models?
I checked the binary source effect and the binary source pattern, but I can't find the best binary source solution. But I didn't check. I have not yet. I have not checked all all possibilities about of the binary source. So I should check.
Event, and I find that it is disfavored by delta chi-squared of 50. So, well.
Okay, Andy?
No, with point sources.
Okay, now a question by Andy.
So the timescales varied from 4 to 7 days, if I remember, which probably means that the source fluxes also varied by a factor of 1.7. And so then there should be different source fluxes in the diagram, and maybe some of them are closer to the main sequence.
You mean the source?
Right, you've shown one source magnitude, but if the timescales are differing by so much, then the source fluxes are also probably differing by a lot.
Yes. You mean the source flux of each model is different?
Just naively, I would guess it would be, lower by half a magnitude or so, and so it would come closer to this HST relation. Anyway, it's just a guess. So it should be, the different source fluxes should be put on this diagram.
So this number, IS or more RS should be different for different models.
Yes. Yes. This estimate is using wide one model's source color and source flux. So this parameter is derived is only wide one model. So
so the question is if you use the different values for different Bayesian analysis for all 5 models.
Yes, I use all. Sorry.
Okay. So we're figuring this out. Great. So let's thank Iona again. And now, next speaker is Shude Mao. Will tell us about statistics.
Hello. So I'm delighted to have a chance to talk to you about application of astroseismology and Gaussian processes to microlensing in this particular case discovered by the OGO collaboration. I hope these 2 techniques can find much wider applications in the future in the microlens field. All the work has been done by my student, PhD student Shunsen Li, who cannot be here due to a visa problem, Wei-Chen Zhang, who is here today, and many other people, including some in the audience, and survey and follow-up teams. Okay, so if you look at this event discovered by OGO collaboration, you have 9 years of data on the left, and the microlensing episode occurred in the 8th season. Now, if you look at the baseline of this light curve on the right, and I have amplified the 7th season baseline, you can see the event shows intrinsic variabilities, and this shows OGO data together with KMT data. So the event is clearly variable on the scale of 1%, 0.01 magnitude. So this sort of intrinsic variability has to be taken into account in microlensing observations. In fact, I think such variabilities are very common in stars and also red noise in observations. Michael mentioned that whether one is worried, I'm always actually a little bit worried when you discover microlensing planets, when the signatures are very subtle, whether such correlated noise or intrinsic variabilities can manifest as microlensing planets. Now, the second challenge in modeling this event is due to the low latitude of this event. So you can see the latitude is about minus 1.84 degrees. So it's very close to the galactic plane. So the dust extinction will be complicated along the line of sight. In fact, we have two other events as shown here, one studied by Dave Bennett and one studied by Yosei. And the one studied by Yosei is very close to the plane. It's minus 0.33 degrees. So this shows that events very close to the plane. Of course, the dust extinction along the line of sight can be more complicated. Such events will be much more common in the future, for example, for the prime telescope Taka discussed and for the WFIRST survey in the future. So thus introduces complications in determining the lens and source properties, their distances. So these challenges have to be met in order to understand the lens and source configurations. And as you know well, the source distance and other properties are very important for understanding lensing geometry. So if we know the source angular radius combined with the finite source size effect, we can determine the lens Einstein radius. And if you have parallax, we can determine the lens mass uniquely. Now, in most cases, the source distance is assumed. But if somehow we can determine that the source distance, then combined with the parallax and the finite source size, we can determine the lens distance uniquely as well. And this is important if you want to study, for example, how the lens is partitioned in the disk and in the bulge. And if some of these lenses have planets, then you can study the planet formation efficiency in different environments, like in the disk and in the bulge. So how do we overcome these issues I mentioned? So the first problem is intrinsic source variability. So the usual chi-square minimization is written here. So this is just the difference in the observed flux and the predicted flux. So we can use Gaussian processes to take into account the intrinsic variability, and it's actually fairly straightforward. So RT is basically the vector formed by the difference between the observed and the predicted quantities. So for n data points, this will be a vector of n rows. And we take into account the intrinsic variability by a matrix of K. This is correlation matrix. So this is n by n correlation matrix, and the matrix element is written here. So you can see this has the first term contains an exponential term and a cosine term. The cosine term basically takes into account the quasi-periodic variations, and the first term is exponential. So this parameter omega naught controls how wide the data points can be separated and can still be correlated. So the last term is the usual data term. So this is a diagonal term of the covariance matrix. So if this term is 0, then you only have diagonal terms, and the whole thing converts back to the classical chi-square minimization. Now, this term takes into account the intrinsic variation. Omega naught is, again, controls how wide separated two data points can be, and they are still correlated. And S0 is an amplitude parameter. So this is the simplest model we can consider in correlated noise or intrinsic variability. You can add in more parameters to take into account correlations on different timescales. So for our purpose, we only use one of these frequencies. Now, so this shows the model without intrinsic noise and with Gaussian processes. So the data points here in red shows the Spitzer data, and the ground-based data are shown in many different colors from different collaborations. And the traditional method gives the residual as shown here, you can see clearly that there are still systematic trends. But once you take into account the Gaussian process, the residual shows no systematic trend. So in this event, we clearly detect both parallax and finite source size effect. So let's look into the parameter uncertainties. So this is the usual conventional chi-square minimization, and this shows the Gaussian processes. So in fact, most parameters are very similar to each other. But if you just look at one parameter, for example, the flux contributed by the blend, you can see the parameters are somewhat different. But one thing you notice, the error bars in the Gaussian process are much larger, by a factor of 3 for this parameter. And this basically reflects the fact that we really don't know the source intrinsic flux very well. And the source shows complex variabilities. So in the same vein, if we have intrinsic red noise or red noise in the measurements, the error bars will also be larger. So if we don't take this into account, the error bars we quote may be misleadingly small. Okay, so how do we take into account the second problem in terms of the dust, the source distance? For this event, actually, we are very lucky. If you look at the light curve carefully, the source is quite bright. The I-band magnitude at the baseline is 14th magnitude. So the OGOR photometry is very accurate. It allows us to do seismology. And for example, for this red giant star, this is a Kepler seismology. So when you do a Fourier analysis of a time series, you get a power spectrum as a function of frequency. Usually you get a maximum peak with maximum amplitude corresponding to a frequency nu max, and many distinct Fourier peaks. And the frequency difference between adjacent peaks is written as delta nu. And this parameter is related to dynamic time in the star. And nu max is usually related to sun crossing time scale in the pressure scale height. In any case, you can see these two parameters are related to stellar parameters like stellar mass, radius, and effective temperature. So from such spectrum, you can infer the source mass, radius, distance, and as a byproduct, also the angular radius. So we can apply this to this particular red giant star. So this is the power spectrum as function frequency. We can infer this parameter nu max quite well, combined with its color, and also comparison with Kepler red giant source catalog. We can determine many source parameters, including effective temperature, log G, metallicity, which is close to the solar, and the mass is about 1.45 solar masses. The radius is quite large, about 67 solar radii. And the one quantity that is interesting is the source distance is 11.5, so it's behind the bulge. In fact, the source is so bright, we have Gaia probe motion, so we can multiply the source distance to obtain the linear spatial motions. So the L direction motion is minus 222 kilometers per second. Basically, it's consistent with being counter-rotating on the far side. So we infer that the background star is actually conforming to a disk star counter-rotating in the opposite sense relative to the sun. Okay, so we can infer the source radius. So this is from seismology analysis, and this is from the color surface-to-price relation from this paper, and this is from another paper often used in microlensing studies. You can see that this is about 2 sigma away from the seismology analysis. So what's going on? In fact, this analysis assumes the V minus K colors should be smaller than 2.5. Our source is actually much redder with this color index of 4.4. So this often used formula doesn't apply to our source. So for simple theories like myself, one should always be aware that sometimes these empirical formula may not apply to your source.
Well, you could read the Corvella paper where it says it doesn't apply to giants.
That's right. But sometimes theories like myself don't read the papers. We just use the formula. Okay, so let's look at the models more carefully. So in fact, we have the usual fourfold degeneracy. So in terms of chi-square, the 4 models differ by only 5. So this model is actually formally the best, but the chi-square difference is too small. So the parallaxes are somewhat different. If you use the rich argument, this solution and this solution with smaller parallax are slightly preferred by a factor 2.6, but this is not convincing. Now, you can, in fact, determine the length distance using the procedure I mentioned at the beginning. We know the relative prop motion, and we know the source prop motion, so we can infer the length prop motion. Since we know the length distance, we can infer the length motions in linear dimensions, and we can use the length distance, length velocities in Bayesian analysis. We can obtain the probabilities of the length being in the bulge and in the disk. And these models also give the posterior probabilities of these various models. So in fact, this model, minus plus solution, is preferred by the posterior probability. So if you weigh the bulge and disk probabilities by the posterior probabilities, you find that the length is quite likely to be in the bulge with more than 80% of probability. Okay, so my time is up. Let me just put on my slide. I want to say the source is likely to be an M2 giant in the far disk because of distance and kinematics. And the length mass is likely to be a brown dwarf if it's at 9 kiloparsec, and slightly more massive, maybe an ultra cool dwarf at about 10 kiloparsec. The length is like in the bulge. I just want to end the talk by saying that geosseismology is very useful to derive properties for bright sources, and Gaussian processes can be used to tackle intrinsic variabilities or correlated red noise, and both will become more important in the future, particularly for WFIRST, as Andy estimated, maybe 1 million sources will have seismology analysis results. And on that optimistic note, let me finish my talk. Thank you.
Thanks, Shude. Nice work, Dave.
So actually, there is another Crivella paper also from 2004 that's appropriate for giants. It's based on Cepheids. It would be worthwhile to check if that actually fits with your measurements. And then my question is, in your list of the results of the Bayesian analysis, you didn't include the source distance, right? So you estimated the source distance, but then you didn't multiply it by a prior that might make it more likely to be in the bulge.
I don't remember whether my student took that into account. I think he is probably smart enough. He has taken that into account.
Well, I would recommend adding another line to show what the source distance is.
Right.
Table.
Well, it's written before, so yeah.
Huh?
It was mentioned before, yeah.
Okay.
So I presume he did take that into account, but I need to double check, yeah. Some of the results were produced maybe 2 days ago. Yeah.
Okay.
Mm-hmm. Okay, Eric.
I wanted to go back to the issue of like whether our noise model is appropriate for data. And I see here your chi-squares or of order your n data. Is that because you've already done something to scale your uncertainties, or is your data set somehow much better than many of the data sets I've seen earlier in the...
All right, I didn't mention. So we already went through a complicated error value scaling because in this correlated, the intrinsic variability, the renormalization procedure is actually slightly more complicated, and Andy has helped us in figuring this out. Yeah.
And so then in the slide you showed there were still some outliers. So one thing that people sometimes do is they'll convolve a Gaussian process with something that is heavier tails, like a t-distribution. Have you done any sort of sensitivity analysis of how sensitive things like your bulge odds ratio are to the assumption of Gaussianity there?
About the Gaussianity in the data points?
So it's like, as you mentioned, there's some excess outliers there. So one thing that comes to mind is you convolve your Gaussian process with something like a t-distribution that has broader wings, and then see if you still get the same ratio of bulge and disk solutions, or if that somehow affects things?
Oh, we haven't done that, but that's a good suggestion. Of course, some of these Gaussian processes are widely used in radial velocity and transits. We're just far behind other people. Yeah.
Well, I think there's lots of people who could improve further.
So, Taka.
Astroseismology is very powerful, and I wonder if it depends on the wavelengths and if the applicable to the near infrared.
Maybe Andy, you can answer.
So my answer comes from Daniel Huber, who said that, when I made my estimates, he said that it should be cut down, I think, by 50% or something compared to Kepler-like curves amplitude.
Mm-hmm. Okay, last question, Jessica.
I was wondering on the Gaussian process, do you put it, is your amplitude color dependent? Because, intrinsic variability in the star is usually color dependent somewhat. Or do you assume, and I see you have a mix of filters here, so.
I think we only used one filter. Is that true, Wei-Chen? Yes. I don't know. So actually, my student, Shunsen Li, did this. So
it's all fit to Gaussian. It's all fit to Ogle data.
I think it's only, yeah, right. It's only fit to the Ogle I-band data, because other data sets, somewhat, the data maybe quality are not as good. Yeah, that's a very good point. Yeah.
Okay, let's thank Shuda again. And the next talk is by Akihiro Fukui, and he will talk about Kojima event. So pretty interesting.
Hello, my name is Akihiko Fukui from University of Tokyo. So this is a switch. In the last conference, I showed a preliminary result of our follow-up observation of Kojima event, and today I'd like to show the result of a more detailed analysis. So the so-called Kojima event was discovered by an amateur astronomer, Mr. Kojima, on October 31, 2017. First, as an unknown transient event on a normal star with the V magnitude of 14th, which is located toward Taurus region, which is about anti-galactic center. And microlensing nature was confirmed by subsequent follow-up observations and also assessing all-sky survey archive data. And after that, the detection of planetary anomaly just around the peak was reported by Nushita et al., who estimated the mass ratio of about 10 to minus 4. But because parallax signal was not included in their analysis, they just estimated the lens parameters using galactic model like this. And after the discovery, we started several kinds of follow-up observations, including photometry, spectroscopy, and high-resolution imaging. And for photometry, we conducted intensive observations using a number of small to middle-class telescopes in the northern hemisphere in optical and also near infrared. And also we collected all data during the anomaly and reduced them. Okay, so, and we conducted high-resolution spectroscopy using NAOJ 1.9 meta telescope. One day after the peak, when the magnification was about 10. We also conducted low-resolution spectroscopy using LCO2 meta telescope at 2 epochs during the event. We also obtained AO image in K-band using NAC2 in last February. And this is a light curve we obtained. And our observations lasted for about 3 months, which is much longer than the dataset that Nancy title obtained. But we did not find any additional feature in the tail of the light curve. But we could improve the parameters of the light curve like this, and which was also confirmed by Dave, Valerio, and Etienne using different pipelines. And we also refined the properties of the source star. So from high-resolution spectrum, we estimated the temperature, radius, and metallicity of the source star, which is consistent with late F dwarf. And from Gaia DR2, we estimated the extinction towards the event field. So Gaia DR2 provides extinction and also precise distance of each star. So, okay. We averaged the extinction of the stars in the field and derived the relation between the extinction and distance. And using this information as priors, we fitted the source fluxes, which was obtained by the light curve fitting with theoretical spectra, and derived the final estimation of the properties of the source star, including the angular source radius and also distance to the source star. And we the spectral type of the source star was also confirmed by LCO spectra. So because we obtained spectra at 2 epochs with LCO telescope, we could extract the spectrum of the source star using this formula. And comparing with template spectra, we confirmed that the source star is consistent with late F dwarf. And from light curve fitting, we marginally detected the finite source and orbital parallax effects like this. And from these effects, we weakly constrain the theta e and pi e values. And using these constraints, we weakly constrain the lens mass and distance of the like this. But fortunately, Subo et al. Could measure the separation of the microlens images using VLTI gravity, which is interferometric instrument. So this is a schematic of the sky plane, and the lens is at the center, and the source is here. And they measure the separation of these two microlens images. And from this measurement, they could constrain the theta e value very precisely. And they also constrain the direction of pi e in 2 directions. And using this information as prior, we refitted the light curves and refined the parameters of theta e and pi e. And we constrain theta e very precisely. And on the other hand, for pi e, we could reject one of the 2 solutions, directions. But we refine the pi e values by a factor of only 2. So this is a defined constraint region of distance and mass of the lens star. So on the other hand, we could detect blending fluxes in all optical and near infrared bands, which basically can be attributed to the lens star. Because from Keck AO image, imaging, we did not find any background contamination. And also, high resolution spectrum excludes companions to the source star. And the light curves show no additional feature due to the companions to source or lens stars. So using these lens brightness and up-to-date empirical mass luminosity relations, we measured the mass and distance of the lens star, which is indicated by red region, and which is fully consistent with the result derived from theta e and pi e. But the uncertainty of stellar mass is much smaller than becomes much smaller, and we combined these two measurements and derived the final solution, which is indicated by green region. So we found that the lens star is located at about 500 parsec, and stellar mass is about 0.58 solar masses. Planetary mass is about 20 Earth masses, and the projected separation is about 0.9 AU. And I would like to emphasize that planetary mass is measured with only 10% error. So this is the location of this Kojima event in the semi-major axis normalized by snow line and planetary mass plane. So this planet is Neptune, just around or even in the snow line. So and actually this is a innermost Neptune among the all microlensing Neptunes. And this region has been less explored by any methods. And we also calculated the detection efficiency of this event, which is indicated by contours. And we found that detection efficiency of this planet is about 40%, and which may imply that Neptunes are common around the snow line as well. Okay, so this is a summary and the future prospects. So we defined the parameters of the Kojima event from our follow-up observations and direct theta measurement by Subo et al. And we found that the host star is an early M or late K dwarf at 500 parsec, and the planet is Neptune around the snow line. And this event is exceptional among all planetary events in various aspects. For example, the source star is the closest and the lens is the brightest, and the planet is actually the hottest Neptune. And the planetary mass is determined with 10% error. And because the host star is very bright and will soon be separated from the source star, probably in 1 year, we could get direct spectroscopy of the host star and could conduct RB confirmation of the planetary mass and orbit in the future. Thank you.
Questions? Don't see any questions. Everyone is processing this great event. Okay, Taka.
So just comment, this radial velocity amplitude of 2 meters per second is just expected accuracy of the IRD instrument on Subaru.
Yes.
So marginally detectable if we have a many of measurements.
Yes, I expect that, yeah.
Any more comment? No? So let's thank Akahiko again. And the last talk of the session and of this day is by Gabriela Navarro about the VVV.
Thank you. Okay, hello everyone. My name is Gabriela. I'm doing my PhD between Chile and Italy in Andres Bello University and Sapienza University in Rome. And I will show you some results that we found using VVV data. So I will briefly introduce what is the BVV. So we use like the VISTA telescope, that is a 4-meter telescope. The field of view of the Birkan camera is 1.5 degrees square, so it's pretty big. And the important thing of this survey is that we are observing in the near infrared. So we can go through the dust that is in the center of the galaxy, and we can study objects there. So this is the area of the VVV. So you can see that it scans the bulge and also one part of the plane. And I will center my studies in the bulge. So those are the tiles of the VVV. And I will center my search of microlensing in this area, in the very center. So why I decided to do this is just because I was searching for variable stars, but I found some microlensing events. And then, like based on this plot, there is the number of events that we find with latitude and longitude. We expect to find, I think, a lot of microlensing events toward the galactic center. So this is more or less this is an extinction map of Oscar González. And you can see that the dark area is the most extincted area. So I just got the data from here. But the important thing is that I use PSF photometry, because the aperture photometry that is from the survey is not enough to study this area. So I use the PSF photometry, and the detail is in this paper. So basically what I did is just I compute like a code that detects automatically some candidates, and I just use some relations in each of the light curves of the photometry obtained, and I obtained some parameters, and the parameters are at the end with a quality number that is related to the probability of this event to be a microlensing event or not. And the important thing is just to check is that this is the camera. So you can see that there are some gaps there, and the observing strategy of the VVV is to move the gaps to fill the empty spaces. The name is a pop print, so it does it like 6 times to fill the spaces. And so there is a superposition of some areas, and I tried to find if I found 2 times the same microlensing events, some repeated events. So I put these constraints in my final sample, and we found some 40 repeated events in these areas. So the idea is more or less this one. So these 2 events here are 2 different events found in different pop prints. And then if we combine the data, you can see that it's probably the same event. Then I obtain the parameters using all the data, so they are better constrained. So the first final sample is almost 200 microlensing events in the very, very center of the galaxy. You can see here the map. This is, again, the extinction map in the background of Oscar González. And then you can see that all of these events are new, because we, for example, Ogle and Moa cannot reach the very center. So with the VVV data, it's possible to obtain this. But I have to say that this survey is not for microlensing. So now I will discuss some details, some important details. But this is the first sample that we obtained. So then this is the first sample. So then I extended the area, and I did the same procedure. So we passed from here, that is all the first sample that we had, that is time and magnification. There are all the light curves plotted together. And we found 630 events in the 5 years of the VVV survey. So more or less in numbers, we started from 10 to the 7 events. Then with these codes, we obtained 5 times 10 to the 4 light curves. And then I did a visual inspection of all the light curves, and I obtained the final sample. So this part is, of course, super time consuming, and I'm sure there is another better way to do it, but this is the only way that I could do 1 or 2 years ago. So then these are all the candidates. So then when I plotted the quality number obtained with 2 different models, I realized that all the real microlensing events are concentrated in a small area of the plot. So now for the next step, maybe we can, if we can extend the sample again, we can just reduce and make a cut in the quality number, and we should analyze a less amount of events. So this is the number of observations during the complete survey, and this is the number of events found during the same time. So you can see there is a relation between them, and this is, of course, this is what we expect, but this is important because we realize that the detection of microlensing events is directly related with the observations. And as you can see here, the observations of the survey are very patchy, and the cadence is not really good. So this is, I mean, all the time that we have a big amount of observation, we found some events. And this is more or less the same. This is the different tiles that are the different areas. So this is the observations, and again, this is the time of maximum magnification of each event. So you can see that both plots are quite related. So then, based on this, I decided to do a analysis, like a sampling efficiency, because of course we are not going to detect very short timescale events because we are observing like one observation per night at best. So what I did, I created some Monte Carlo simulation of fake microlensing events and using the observation of each tile. So just to explain a little bit the plot, the white lines, the white vertical lines are the observations of the VVV for each tile because they are quite different. And then the colors are the microlensing fake light curves. So what I did is just to create a huge number of light curves, and then I tried to see if my program detected them or not. So then I obtained this plot that is the sampling efficiency that is related to the, it depends on the Einstein ring crossing time, and the colors are the different areas of the area of the VVV area studied. So what is important here is that the VVV is really, really bad at detecting short timescale events. So for planets, it's not useful. But for long timescale events, maybe it's a powerful tool because we expect to find a lot of long timescale events in the galactic center. So this is the color magnitude diagram. I selected the red clump sources, and I compute the timescale distribution. But this is another story, like difficult to analyze because with a lot of studies of the VVV, we realized that we are discovering sources in the far disk, in the other side of the bulge. So of course, our timescale distribution is contaminated. So I don't know how to study this, but if you have any idea, I will be happy to discuss it. Also, I detected that the timescale distribution changed if we move in different latitudes. So if we approach to the center, the timescale distribution decreased. And this was found before by Łukasz, but this is a trend that we expected to find in the very, very center. So this is the map of the 630 microlensing in pink, and the MOA and OGLE microlensing events between the same time of the survey, of the VVV, like between 2010 and 2015. So this is a movie, but I think I don't have time to. This is just a movie to show to the people that it's not in the top in the field, but you can see it's pretty nice because you can see this is of course this is not how we will look at, but you can see the flashes of the different magnifications during the time. The intensity is related to the amplitude, and the duration of the flash is related with the time scale. So also we found an asymmetry on the distribution. We found like the 60% more of events towards negative latitudes. And also if we correct this for the completeness map of Elena Valenti, especially for the VVV, we can guess that maybe this asymmetry is related with the inclination of the bar. Apart from this sample, we found a lot of other objects. And for example, this is we found a lot of incomplete microlensing events that we took out from the sample because, for example, in this case, you can see the first part of the event, but the other part you cannot, you don't have any data, so it's not possible to constrain the time scale, so we left them out. And also, we found maybe some binaries, but of course, this is difficult to fit because of the cadence of the BBV again. But Etienne Bachelet with PyLima, he fitted, for example, this one, and I think it's a very nice fit, but of course, to constrain the parameters is quite difficult. So then the spatial distribution, you can see again the same plot like that before, but these are the complete sample, and the squares are related to the time scale. So the biggest square are longer time scale events. I will skip this because it's not important. And we found also some parallax, some long time scale events showing parallax. So we have a lot of data that we haven't analyzed in detail yet, but if you are interested, we can discuss it. And we found just a few of short time scale events like this one, like a few days, less than 10 days. And this is more or less the summary. We found a new microlensing event because it was a new area. We found asymmetry in the distribution, and also we found some long time scale events, some events showing parallax and so. And for the future, we have a VVVX, that is extension of the VVV survey. So it's taking data from 2015 until 2020. So it's taking data now. So it's interesting also to maybe to follow some long time scale events, or maybe if you have any idea, it's very welcome. Thank you.
Jessica?
Can you go back to your spatial distribution plot?
Yes. Oh.
That one. No, you passed it. Sorry, the one, the boxes.
The boxes, okay.
And can you say what's happening on the right side to produce all those long duration events?
No, actually I can't, because this is quite new. This is the final sample, but we have some long time scale events, and it's interesting to go then to try to see what is going on. But the only problem is that if we need more data, for example, to constrain the parameters better, it's quite difficult to get data in the very low latitudes. So yeah, now I mean, if you are interested, we can talk about it. But yeah.
Okay, Andy.
So, is it possible for you to alert on these events in the future by running your algorithm faster and using those things that you said?
Yeah.
And then you could get denser light curves if they're infrared telescopes.
Yeah, I think it's a really good idea. We try to do this because the at the beginning they try to like add alerts, but at the end I don't know why it's quite difficult to add this to the survey. We have like 1 month of delay from the data to obtain like the aperture photometer. So then everything is quite slow, but of course alerts would be like the solution. Yeah.
Nathan.
I just had a question about the instrument. What's the readout time and characteristics for the camera? You could design a really nice survey with this instrument.
Yeah, I'm not sure about it. No, I don't know, but I know that the limit in magnitude is like 18 more or less, so it's pretty deep. And there are a lot of studies of the BBV that for example, you can see in the CMD a double red clamp that is the red clamp of the other population. And it's very interesting to see how far it's going. Mm-hmm.
Taka?
So if the prime start issuing the lot in real time, is that the BIST telescope will be available for the follow-up?
Yes. No, yeah, it's a good question. Actually, yes, because the strategy of the BBVX is different. So now we have some free time to use it. So if you have, actually, this is very serious. If you have something there before 2020, we can observe it. Like we have the time. So.
2020, it's turning into an optical telescope, right?
What?
What in 2020 it's turning into an optical?
No, but this is the time of the survey, so we have time for. I mean, we also can apply for the Chilean time if it's necessary, but the time of the survey we have observation until 2020.
So just to comment, it's turning into a multi-object spectrograph.
Moons, yeah.
Okay, let's thank all our speakers for this session. And I give the mic to Dave.